In the previous video of this series, I have discussed about how to use the concept of kilomole in the combustion calculation of VOE examination for converting the molecular formula into the mass-based formula, or rather the mass ratios in a combustion reaction, and to calculate how much oxygen would be required for combustion of 1 kg of carbon to produce CO2 or CO, or for that matter the similar way you can also calculate how much oxygen would be required to convert hydrogen into H2O, how much H2O, and sulfur into SO2, the combustibles. In this video I am going to discuss about how to use the concept of kilomole if a gaseous fuel is given. So to calculate the mass or the volume of and the mass of oxygen required for the combustion of a gaseous fuel, how to use the concept of kilomole. Okay. Now for that we need to first understand the Avogadro's gas principle. Now what does it say? It says that if we are having a mixture of gases and if they are at the same pressure and temperature, all the composition of the gas, and naturally if I let us say take flue gas, then flue gas at a pH outlet temperature of 130, 135. So or whatever the composition of the gases, in flue gas you are having various gases, right? Nitrogen primarily, then CO2, then some amount of H2 will be there. If sulfur is in the fuel, then SO2. So all these gases are at same pressure and temperature, and if that is there, in that case the equal number of molecules of each of these gases will occupy equal volume, right? That is what Avogadro's gas principle says. Now how to come to this understanding? So let us say we take the ideal gas equation, which is PV is equal to nRT, and we put this ideal gas equation in the flue gas. In the flue gas, let us say we have got the CO2 and N2. Definitely N2 will be much in larger quantity as compared to CO2, but they are at the same pressure and temperature. Let us say the pressure and temperature is P and T, and let us assume that N2, which is more, is having N1 kilomole of nitrogen, right, and it is occupying a volume of V1, and CO2 is having N2 kilomole of nitrogen and it is occupying a volume of V2, right? Now if I put the Avogadro gas principle on both these gases, for nitrogen it will be PV1 is equal to N1 RT. R is universal gas constant, same for all gases, and P and T is same for both the gases. And for carbon dioxide it will be PV2 is equal to N2 RT. Now if I have these two equations, and algebraically if I divide equation 1 by 2, what do I get? I get this R, T and P gets cancelled. So V1 by V2 is equal to N1 by N2. That means the volume is proportional to the number of kilomoles or number of molecules, right? That is what Avogadro's gas principle says, that if now N1 is equal to N2, then V1 will be equal to V2. That is Avogadro's gas principle, right? Now this principle can be used to find out couple of very useful informations. For example, let us say at NTP somebody is measuring the volume of hydrogen, nitrogen and CO2. Now when he measures the volume of 2 kg of hydrogen, and we know that in 2 kg of hydrogen means is the molar mass of hydrogen, that means the number of molecules are 1 kilomole. He found the volume as 22.4 meter cube at NTP. We have discussed NTP in BOE at least means 273 Kelvin and 1 standard atmospheric pressure, that is 101.3 kilopascal. Now at the same NTP, if we now measure 28 kg of nitrogen and 44 kgs of CO2. Now what is the similarity between 28 kg of nitrogen, 44 kg of CO2 and 2 kgs of hydrogen? Both are the molar mass. All three are the molar mass of these three gases, right? So the number of molecule is 1 kilomole and we are measuring at NTP, right? So at NTP the temperature and pressure is also same. So the volume is going to be 22.4 4 meter cube for both of them. So we know the mass, we know the volume at NTP, so we can calculate the density of any gas. The molecular weight of which is known to us, that means the molar mass is known to us as is molar mass by 22.4 kg per nm cube, right? This helps us in lot of calculations in BOE. Okay, now this 22.4 meter cube we can come mathematically also using the same ideal gas equation PV is equal to nRT at NTP. If I say take 1 kilomole, right, so N will become 1. So in this case the volume will be is equal to RT by P, N is 1, right? Now when I am having at NTP we know the R, that is the universal gas constant, right? So that is 8.3143, and we know the temperature is 273 Kelvin and pressure is 101.3 kilopascal. So RT by P will be calculated as 22.4 meter cube. Okay, so density of any gas at NTP can be calculated this way. Now in combustion calculation, how it is used? Let us say I have a requirement that I need to find out the stoichiometric air required for the combustion of 1 nm cube of CH4, which is a gaseous fuel, and I need to find out this air in both volume as well as mass, that is in nm cube as well as kg, right? These sort of questions are quite often coming in BOE. Now yes, we need to know certain basics of combustion calculation, but in combustion calculation always first focus on the oxygen requirement, right? Now CH4 is a hydrocarbon, and we should know this for a fact that any hydrocarbon with oxygen will react completely and the result will be CO2 and H2O. So first write down the reaction, molecular reaction. Once you do that, because once the gaseous fuel will be given, right, the hydrocarbon gas plus O2 will be CO2 plus H2O. Only thing is now you need to balance. So how to balance? You see on the left hand side of the equation 1 atom of C, on the right hand side of the equation 1 atom of C. So it is balanced. Hydrogen is 4 atoms on the left hand side but 2 atoms on the right hand side. So we gave 2 H2O. Now hydrogen is balanced. The resultant oxygen on the right hand side is now 2 for CO2 and 2 for 2H2O. So total 4 oxygen is required. So now I make it 2O2. Now the equation is balanced. So what does this equation says? It's a molecular equation. So it says that one molecule of methane is going to react with 2 molecules of oxygen. The result will be 2 molecules of H2O and 1 molecule of CO. Okay, so now we know how much oxygen is required for 1 molecule, and if I say in nm cube, if I want to calculate, right, and nm cube means NTP means the temperature and pressure is constant for these gases, right? So I can say using the Avogadro's principle 1 nm cube of CH4 is going to require 2 nm cube of oxygen, right? And suppose I want to find out the mass of air. So if you want to find out the volume of air, you find the volume of oxygen, so in nm cube of oxygen. If you want to find out the mass of air, you need to find out the mass of oxygen required for 1 nm cube of CH4. So in this case 2 nm cube, we know the density of oxygen at NTP, right? So that comes to 2 into 32 by 22.4. 32 is the molar mass of oxygen. So molar mass by 22.4. So we can calculate 2.86 kg of oxygen. So now we know the oxygen required for combustion of 1 nm cube of CH4, both in nm cube as well as kg. Next, we need to understand that in combustion calculation we assume that air contains 21% of oxygen by volume and 23% of oxygen by mass. Okay, so if I want to find out the volume of air, I take the volume of oxygen, and considering 21% of oxygen is there in air, I will require 2 nm cube by 0.21, that is 9.52 nm cube of air. And if I want to find out the mass of air, We have already calculated the mass of oxygen required for 1 nm cube of CH4. So that mass divided by 0.23 will give you the mass of air, right? That is how we calculate the air requirement. Stoichiometric air requirement means the minimum air required for complete combustion. That is how we calculate this thing, right? It's pretty useful, particularly in dealing with gaseous fuel. Another very useful understanding, once you understand that the volume, that means Avogadro's principle, that the volume is proportional to the number of molecules. So suppose they are giving us a fuel analysis, and gaseous fuel analysis will always have individual gases in percentage, right? In ultimate analysis we get percentage. Now when they say percentage analysis, it can mean both, that if I'm having 20% oxygen, hydrogen, 45% CH4 and such, right? 10% C2H6 and 10% C3H8, balance 15% is C4 plus. That means, it means that in 1 kilomole of this gas, this refinery fuel gas, I'm having 0.2 kilomole of hydrogen, 0.45 kilomole, right? Because the number of molecules if I take, right? So it's a molar proportion. I also understand that 1 nm cube of this fuel will contain the same proportion of hydrogen, CH4, C2H6, C2, C3H8 and so on, right? So the molecular proportion, because P is your proportional to V, so naturally we get this understanding. And with this understanding, we can calculate another thing. Suppose I am having a flue gas composition. The mass of flue gas composition I can calculate, right? I will deal with this in the next video, how to calculate the mass of flue gas composition using the same kilomole to mass concept, right? Now, if I know the mass of flue gas composition, I can convert it to the volumetric composition, or at least we can find out the volumetric analysis. What we need to do, we need to just convert the mass into kilomole, and whatever the kilomole proportion is the volume proportion, so we can calculate the volumetric analysis of a flue gas composition by that. A question like this, suppose I take a question like this as in Assam BOE 2022, right? They have given you a fuel analysis, that is the ultimate analysis. Now they are asking you to calculate, they have also given you the air to fuel ratio, that is 12:1. Now they are asking you to calculate the mixture strength as a percentage rich or weak, right? Rich or weak means if it is weak, that means it is less than stoichiometric air, right? The minimum theoretical air, it is less than that. Or if it is rich, that means if it is having more air than the stoichiometric air. And the second thing they have asked is volumetric analysis of the dry product of the combustion. In my next video, I might be dealing with this particular, I will start with this, how to calculate this kind of questions, right? So carry on watching the YouTube channel of indiaballer.com, and till next time, thank you very much. See you, bye.